Sorry.
Just a moment. Because
I didn't want that. I have to do, okay. All right.
okay, so I think that now we are on live. So welcome everyone for the last talk of the seminar for students or for graduate students in probability. The idea of this seminar is that active researchers present one of their papers in a way that students can understand.
Good morning. We are happy that Anita Behme is today in our seminar, and she is from 2016 professor at Technical University in Dresden, and actually it's currently the director of the Institute of Mathematical Stochastic at TU Dresden University. And she is generally interested in Lévy processes, Orsten-Uhlenberg processes, and Markovian process in general. And today she will talk about downward passage times for spectrally negative Lévy process. Thank you, Anita.
Well, thank you very much for the invitation. Yeah, as it was already said, I will talk about downwards passage times for spectrally negative Lévy processes. And of course, I have to mention that this is joint work with my PhD student, Philipp Striezel, who has done a lot of computations for this project. And well, as I know that you already heard a lot about this topic in a previous talk, so I will rather quickly go through the details that you already know, but still I have, of course, to set the notation and so on. If I'm too fast, please interrupt me. And then in the second half of the talk, actually the slides will be empty and I will be writing, so it's gonna slow down a lot. Okay, so what are we doing here? As it's written, we want to consider a spectrally negative Lévy process. This will always be called X. Xt for t larger or equal to 0. And this spectrally negative Lévy process is uniquely described by its so-called Laplace exponent, which is this one here. So it's always going to be a psi. And it's the same as taking the logarithm of the expectation of e to the theta x. And if you look very closely, actually, to be a true Laplace exponent, we should have a minus up here. Right, so there should be a minus, but it's not going to be there because we are dealing with spectrally negative Lévy processes. And so this is not a typo, it's as I want it. Okay, so this Laplace exponent then looks like this. So we have three components here. First of all, yeah, a sort of drift term, then some Brownian motion term, and then the jumps. And the jumps are described by a measure pi, which lives on the positive half line. So what I do here is I write things up such that the measure lives on the positive half line, of course, but still the jumps are negative, right? I just want to avoid too many minus signs in my computations. Okay, so this Laplace exponent has a generalized right inverse, which I write as phi of q. So this is the supremum of all theta such that psi of theta equals q, just a standard right inverse. Okay, and so what do we want to do? We want to talk about downwards passage times. So we want to talk about what I write here as tau x minus. This will be the first time that the process xt drops below the level minus x. Okay, so I made a picture here, or actually two pictures. So the process that we look at could be of finite activity. So that would mean I would have no Brownian motion and only finite intensity for the jumps. And then it would be such a process which looks like a typical risk process. And that's also one of the motivations to consider such times, such downwards passage times. So you would have some like premium income, linear, and then having to pay for the claims. And then in this interpretation, tau x minus would just be the ruin time, given that you start in x. Here in our general Lévy setting, we start in 0, and that means that we hit minus x. But since we are space homogeneous, it doesn't make a difference. And of course, since we allow for any spectrally negative Lévy process, it could also be a Brownian motion, and then it might look like this one here. And in this case, we would just creep below our given value minus x, whereas for the case with jumps, we might actually jump over the given value. So it makes a difference that we really look at passage times and not just hitting times, because we might actually not hit minus x. All right. So what we exclude here throughout is the case that x might be a pure drift. So I would have no Brownian motion part, no jumps, but then it's a very boring problem. So I won't say that anymore, but this is always excluded in all the results. And I will also always exclude the value x equals 0, so hitting 0 whenever my process x is of unbounded variation. So why is this the case? Well, because if you have a Brownian motion part in there or infinite activity of the jumps, actually you would have that the probability that tau 0 minus 0 equals 1. So you will instantly hit the level 0. So it doesn't make sense to look at this. And so this case will also always be excluded, even if I don't say it anymore in the following. Okay, so that's our setting. And now, so what do we want to do? This is the quantity I'm interested in. And well, of course, it's not so easy to just write down what the distribution might be. And so what we will focus on here are moments of this first passage time. So in particular, I want to study whether moments exist and possibly get formulas if they exist. But actually today I will focus on the question of if moments exist. So like expectation, variance, and so on. Okay, so how can we start to study our first passage time? So there's a given fact that you can find in any textbook on Lévy processes, and which says that actually the Laplace transform of this first passage time, well, kind of conditioned on the fact that it's finite. Well, there's a formula for that. And this formula uses the so-called scaled function of the Lévy process x. So the scale function WQ is a function which is 0 on the negative half line, and on the positive half line, it's defined via its Laplace transform. So you see here again this Lévy exponent popping up again. And of course, this denominator should not be 0. So we can only write this down for all beta, which are larger than. Now here's the right inverse of the Laplace exponent. So if beta is larger than this right inverse in Q, that means that psi of beta minus Q will not be 0. And this uniquely defines me the scale function WQ. And a part of the scale function one also needs, it's the integrated scale function, which is more or less its primitive. So, well, you have to integrate up the scale function up to x, multiply with q, add a 1. And then you can, with these two functions, you can now write down this Laplace transform of the first passage time, as it is written down here. Well, and that's already quite helpful. And you can easily find some direct consequences of this. For example, you can let, in this formula, you let Q tend to 0. And what you see is that actually this part here will vanish, and all you are left up with is the probability that tau x minus is finite. So the ruined probability, actually, or the probability that you ever hit this level, minus x. Well, and on the right-hand side, this is what you would get. And one already sees that here, so this is the maximum, that if this psi prime of 0 plus, which is actually the same as the expectation of our Lévy process x at time 1, if this is positive, we will get something which is less than 1. And if it would be negative or 0, this probability will be 1. Okay. So we can do something more with our formula star here, up here. We can also differentiate it. So if you differentiate on the left side, and well, things go right, so you can plug in the differentiation into the expectation. What will happen is that every time you take the derivative, you will get, so the derivative with respect to q, of course, you will get a tau x minus in front of this e function. And this will end up like this. So you take the case derivative with respect to q, you get a formula like this. And then again, you can let q tend to 0. And what you will see is that actually you get a formula for the case moment of tau x minus in this form. So as a limit of this case derivative of this term here. Okay. So far, that's not very difficult. So now you can also do this actually more generally by using fractional derivatives. So don't worry about these formulas here. It's just a version to define a fractional derivative, which does what we want to do. So now we can write down more or less the same thing. Now for any kappa, which is larger than 0, we get the kappa's moment of our first passage time, given that it is finite, in this form. Okay, so now you need the kappa's derivative with respect to q of this term, and then still take it in 0. Okay, from this formula, you can actually now start to derive formulas for at least for integer moments. It's possible. It takes some time and you have to evaluate this, and you might, well, now it depends on whether you know what your scale function is, but there are cases where you can write down a scale function and then you can also work this out. It's a bit tedious, but it's possible, but I will skip it here. Okay, but so because I wanted to talk more about existence of the moments, and well, from this formula now we know that, well, the left-hand side will be finite if and only if the right-hand side is finite. So and when is this finite? Well, W and Z are actually analytic in Q. So taking derivatives should not be a problem. Of course, one has to take a look at the fact that it's not a standard derivative, but still, it shouldn't be a problem. That's the idea. But what might be a problem is this term here, q divided by phi of q, because we don't actually know what phi of q is, the right inverse of some Laplace exponent. So you saw this Laplace exponent, but there's no closed formula for phi. And now it's even q over phi, and well, so what should this be? So we give this a new name and call this eta. This is q over phi of q. And we realize that the kappa's moment of our first passage time will exist if and only if the kappa's derivative of eta in 0 is finite. Okay. So far, so good. So up to here, this was all rather straightforward, I would say. So you start with a given formulas, you play around with it, And you realize now, okay, everything depends on eta. But how, I mean, this is not a condition you would like to have, of course, because no one knows what eta does. So now I jump to the main result, which I want to explain you in more detail afterwards. So what we prove with this, from this actually, is the following. So we have to split up into 3 different cases. So either we have the case that psi prime in 0 is negative, which means that my spectrally negative Lévy process tends to -infinity on average, which also implies that actually the time that so this tau x minus will actually be almost surely finite. And in this case, I can show rather straightforward from what I told you up to here, that all moments will exist. So, right, so this tau x minus is almost surely finite, all moments will exist. That's a nice result, but it's still not the most interesting. So we were more interested in the other case, that you have a process which tends to infinity on average. So what happens then? Remember, from the motivation that this might be a risk process, of course you would like to be in this case, right? You would like to have a process such that you gain capital on average. And then you are interested in what's happening with your ruin time. So in this case, that we have a process which tends to infinity on average, we can show that this kappa's moment exists or is finite if and only if actually the kappa plus first moment of the spectrally negative Lévy process X exists, which is the same as saying that the Lévy measure pi of X integrates Y to the kappa plus 1. Okay. So far, we only knew that this happens if and only if eta has this kappa's derivative in 0, but so the goal is now to show that this is the same as this condition. Moreover, in the case that we have a process which has expectation 0, where we also know that it's gonna hit the level -x almost surely, because it will be oscillating. But here the thing is a bit more complicated. So what we can show is that actually if you have any kappa such that this integral here is infinite, so that X has no kappa plus first moment anymore, then also the first passage time will have no kappa's moment. So this is one direction of the proof of this up here, but the other direction was not possible, at least not with our means. But what we can also show is that if you have a finite second moment of the Lévy process, then the moments of the first passage time will be infinite for all kappa larger than 1/2. And taking this together means that you will never have a mean, you will never have a variance or anything. So integer moments will never exist. Because either you have the second moment, then you know this. And if you don't, you can put in kappa equal 1 here, and you see that already the mean does not exist. However, there's still, of course, a gap, because we would like to show that actually, yeah, even more of these moments do not exist. But okay, this was how far we got. I should say that this result here, so part 2, has also been shown in a more specific setting by Delban, who did not look at general spectrally negative Lévy processes, but only at the Kramer-Lookback model. So you would just have no Brownian motion and just finite jump activity. So then this equivalence was known. However, the technique of the proof of Delban is completely different to ours. So yeah, the proof has nothing to do with his. All right, so that's our main theorem. And as I said, part one is actually not so difficult. The interesting parts are 2 and 3. And so I would like to give you an idea of the proof of this part 2 and 3. So first of all, of course, you could start to just try to compute these things in a certain way. So you can do that if kappa is an integer, right? You can just start to compute, and actually an analytic proof is possible. So you would, yeah, just use various times L'Hopital's rule, and just it's really tedious and long, and actually it's so long and tedious that we didn't find it at the beginning, which was lucky, because then we started to think about other possibilities to do this. And so something which was also applicable for any kappa. Anyway, so this is possible. So what, of course, we wanted it for any kappa. And now what is the idea? The idea to prove this is to interpret the function eta and we know that also what we know is that the derivative of eta in 0 has to be finite for the first passage time to have a finite moment. So we want to interpret eta as a Laplace exponent of a subordinator. So what is a subordinator? A subordinator is a Lévy process which almost surely is growing. So yeah, there would be no negative jumps, there's no Brownian motion part. And the drift is positive as well. So an increasing Lévy process. Let's say this is called Z. Okay. So if I can do that, if that's possible, then I would know immediately that this limit q to 0 of the kappa q eta of q being finite is equivalent to say that the subordinator has a kappa's moment. And then, well, given I know that the subordinator, I know that this kappa's moment of the subordinator will exist if the jumps of the subordinator are appropriately. So yeah, it's a condition on the jumps of that. And then maybe I can translate this to the condition I want to have. But of course, it's a, well, so why should I have this idea to interpret eta as a Laplace exponent? Of course, I have to explain why this is actually possible. So how can I find such a subordinator? So there's a first fact that we will actually use. If we look at the first passage time upwards, so if you have tau x plus, the first time that xt is above the level x, then it is known that as long as this Lévy process x has a non-negative first moment, which is the case because we are in these cases 2 and 3 of our theorem, then this tau x plus, if you let x run like a time, that's a subordinator. And it's even known that the Laplace transform of this is e to the minus phi of qx. So that means phi of q is actually the Laplace exponent of tau x plus. Okay. That's also something that you can find in textbooks. And the fact that this phi is actually a Laplace exponent, that was also one of the first, well, when we knew that, at least it made some hope that this eta might also be something like a Laplace exponent. but still it was not clear of what. So let's take a look at eta. So eta of q was defined as q over phi of q, with this right inverse phi of the Laplace exponent. And now the idea is, well, since phi is the inverse of psi, I can actually rewrite this q up here and write instead that this is psi of phi of q. Actually very simple, but still took some time to get this idea. And now, well, we can write this maybe as another var phi of q. So this is var phi being just, psi of theta divided by theta. Okay, so we can write eta as a composition of something with a Laplace exponent. That's already a good idea. And now we know that compositions of Laplace exponents, that corresponds to subordination of the related processes. But first of all, of course, I have to clarify that this phi is also a Laplace exponent, otherwise it wouldn't work. So, but phi is psi of theta divided by theta, and we know what psi is, so you can write that down and make some not too difficult computations to see that phi of theta will actually be the same as psi prime of 0, or at least the limit of psi prime in 0. So then what used to be the Brownian part will get something like a drift, and you get some integral of the jumps. Like this, for any theta. Okay. And now, well, this is a Laplace exponent. Yes, it is. So we have some drift term here. We have some jump part here. We will not have a Brownian motion anymore. But what we have is this additional term, which is a constant, a non-negative constant. And this is the so-called killing rate. So this phi of theta is actually a Laplace exponent of a killed subordinator. And we can call this yt. Okay? And assume that y is independent of everything else that we had so far. Okay, so that means I know now that e to the minus theta yt is just e to the t minus t phi of theta. Are you all happy with killed subordinators? Or should I explain more on that? So the killing means that actually the process behaves like a subordinator with this Laplace exponent up to some exponential time with this parameter. And at that exponential time, the process goes to some symmetry state, which is not specified further. Okay. Okay, now we have seen that this little phi is actually a Laplace exponent. We know that capital phi is a Laplace exponent, that was known. And we know that composition of Laplace exponents means subordination. And actually, I'll do that here So what happens now is that if we look at the Laplace transform of tau x tau plus at the time y(t), then we can first of all make clear that, well, this process y, as I said, it behaves like a standard subordinator up to some exponentially distributed time. And this subordinator is y tilde. And then I need that my time is still below this exponential time. This is parameter psi prime of 0. Okay. Well, and now I can condition on y tilde. And then given that I know y tilde, I know that this is just the Laplace exponent or the Laplace transform of tau plus, which is, as we all know now, e to the minus yt tilde phi of q. And so this is just. So now again, we have the Laplace transform of yt tilde and this additional condition here, which just means that this is the Laplace transform of y. And so this should be e to the minus t phi of capital phi of q. Or e to the minus t eta of q. So that means now that this Kappa's moment of my downwards passage time that I wanted to look at, tau x minus being finite, is finite if and only if the derivative of eta, the Kappa's derivative of eta in 0 is finite, and this happens if and only if tau y1 plus has a finite Kappa's moment. So at the first moment you might now think, well, but this should hold always because we are drifting to infinity. But remember, this whole problem is not symmetric because I look at spectrally negative Lévy processes at the beginning. So this will be a time where I creep up, and this is a time where I actually jump below. So it's not symmetric, and we cannot just say that this would always be finite. Although we know that this is always finite if we go to 0, go down. Okay. So, but that's a very important intermediate step now. And at least this condition already looks much nicer than stating something on eta. But clearly now the question is, so when does this hold? So when do we have this condition? So first fact, which I actually already used, but still I write it down here once more. So since we have a subordinator or a Lévy process, we know that this Kappa's moment of a subordinator exists if and only if the corresponding Lévy measure integrates z to the Kappa on 1 infinity. Well, that's known. So now we have identified that t to be this tau plus in yt. Well, and obviously what I need is the Lévy measure of that. So, but that's something also one can look up. So this Lévy measure of Z applied on some Borel set B would be, so you take the drift of your subordinating process, which is sigma square half, and then the Lévy measure of the process tau plus. with that's a nice term actually, and then there's another term which is a bit more difficult. You need the distribution of the process tau plus at time s. So this is a law of tau plus s, this mu to the power s. And you have to integrate that with respect to the jump measure of y, but that's something you know, this is s. This was computed to be like this. Okay. So we need some necessary and sufficient condition. At least that's what we would like to have, a necessary and sufficient condition for the following. So we want this integral to be finite. So what's happening? We have the sigma square half, then an integral 1 to infinity z to the kappa nu tau plus of tz. And then after some rearrangement, we need the following. So this should be finite. So at least we are lucky because both terms are positive. So this will be finite if and only if one of the two terms is finite. And the first of these is actually very simple. Because all what we have here, so this condition looks exactly like this condition. So what we have is that this term will be finite if and only if the process tau has a finite Kappa's moment. So if this is finite, then this would mean that tau s plus to the kappa, so the Kappa's moment of tau plus is finite at time 1, and then it's finite for all times. And that also means that actually the integral 1 to infinity z to the kappa mu to the s ds is finite, because that's another way to write it down, right? So it's just the Kappa's moment of tau plus. All right. But this term obviously is the same as this term. So if I assume that the first term is finite, then I already know that at least this part in here is finite. But that's not sufficient for me because I need something more. I need to integrate this with respect to s. So what we also need to show is that this is actually growing like a, like a polynomial of order kappa. So, so what do I mean by that? Polynomial of order kappa? Kappa could be any positive value. So what I mean is it's a function which is dominated by some term which grows like s to here z. No, sorry, there's a misprint anyway here. So of course this should be dz, and then it should be growing like s to the kappa. That was not so easy to show, but however we managed. And if you know that this is growing like a polynomial of, so this is sort of like behaving like s to the kappa, and then you can insert this here. What you see is that you have an integral s to the kappa pi s infinity ds, and then partial integration. Yeah, okay. So what we now know is that at least something like s to the kappa pi s infinity ds being finite is necessary for our finite moment, and partial integration then tells you that this will actually happen if you have the integral z to the kappa plus 1 pi dz, which is what we wanted to have. The fact that this is not only necessary, but also sufficient, at least in case 2, was the other part, which is not that easy and which I cannot show today. So you need various additional steps here, and yeah, this is going too far. But however, at least I think that from here you get an idea why this might be a reasonable condition. Okay. So we know this process Z, we know how it behaves like, and then actually partial integration tells you that you need one moment more. Okay, so how much time do I have left?
Maybe 10 minutes.
Okay. If there are 10 more minutes, then I can actually also say something on the third case. So where we had this extra condition saying that if you have a finite second moment of the Lévy process, then no moments of the first passage time with kappa larger 1/2 will exist. Because the other case, well, you already saw the idea, but this is actually quite different. And yeah, so I'd like to say some words on this part as well. So what do we do there? Well, we fix any kappa between 1/2 and 1, because as I said, maybe we can, yeah, actually, if you remember from the main theorem, if kappa is 1 or larger than actually the other criterion, which I just showed you, so the idea of the proof will tell us that no moments exist. So we look only at these values, and then if we can show that that for any kappa in this interval, the moment will not exist, it will also not exist for any kappa which is larger, and it's actually covering all. So what can we do here? Well, we've already gained some knowledge on how these things behave. We already know that this moment that I'm looking at is infinite if the moment of tau y1 plus is infinite. Okay, so why is this? Well, that's exactly this step here. We need this integral to be finite for the whole sum to be finite. And if this is infinite, which means that tau plus has no kappa's moment, well, then I can forget about my moment that I want to have. So that's exactly what's happening here. If this is infinite, no chance to have a finite moment of the downwards passage time. Okay, and then, well, actually that was one step before. Sorry, actually I mixed it up now. So what I explained you was the next step. The subordinated process can only have a finite Kappa's moment if the non-subordinated process has a finite Kappa's moment. Sorry, so it was one step further. So this was true because we already saw because of the interpretation of eta. And this was true because we know that the jump measure of this guy includes the jump measure of this guy. And if this is infinite, we cannot have a moment here. So the idea to prove that this Kappa's moment does not exist will be actually to prove that this Kappa's moment does not exist. So how can we do that? Well, we can just try to compute it. Because I told you that these Kappa's moments are just the can be computed by the fractional derivatives. So I can just apply the q's, the fractional derivative with respect to q on e to the minus 5q and evaluate that in 0. And this will give me this moment. Okay, now kappa is below 1, so I just plug in the definition of this Marchot derivative that I showed you earlier, but I guess no one remembers. But this is. So we have this. U to the k plus 1 du in q equals 0. Okay, now you plug in q equal, well, you let q tend to 0, so this will be an integral from 0 to infinity, and e to the minus 5 of q will actually be 1 in the limit. And so we end up with something like this. So kappa divided by gamma of 1 minus kappa. Integral 0 to infinity, 1 minus e to the minus 5 u divided by u to the kappa plus 1 du. Okay, and if you look at this, well, e to the minus 5 of u is not problematic, but what is problematic is that you divide by u to the kappa plus 1. And this is going to be problematic around 0. So this will be tending to infinity, yeah, if kappa is too large. That's clear. And actually you can show that the limit of 1 minus, sorry, not phi, but e to the minus phi of u divided by u to the kappa for u to 0, this is infinite. And if this is infinite, well, then this grows above any level, and we have an additional 1 over u here. Okay, so this cannot be finite, and this will actually be infinite then as well. So, but of course we need to prove this, and to prove this, unfortunately we needed this condition, because we apply L'Hopital and we need one more derivative here. However, if you look at it like this, it seems like this should not be necessary. However, it was necessary for the proof. So there might be some more open space to fill this gap. If one has an idea how to prove that this is infinite, yeah, without using L'Hopital. Okay, but anyway, so this was the result that we have. Maybe I go back to the main theorem. So now we have more or less shown the theorem. So the last step was this part here. And I gave you the idea of why this is a good condition, at least by showing you one direction in some detail, and the other direction is more technical. And well, yeah, so that's it. Thank you very much for your attention.
Thank you for the talk, Anita. Are there any questions?
Yes, I have some.
Okay.
First of all, well, I was curious because in the second case, in the case when the first moment of x is strictly positive, the right-hand side of the equivalency does not depend on x, I mean, little x. So what would that be about? Because it means that if you find some x such that the left-hand side is true, then the left-hand side, the right-hand side, it's true for every x. What would be the reason for that?
Oh, good question. Well, it's not 100% true, because for x, I had to exclude x equals 0 in some cases. But apart from that, I guess it's just a question of scaling. So it's a good question about the intuition of that. So either, I mean, we don't say anything about how large this moment will actually be, right? We just say it's finite. So it seems like this finiteness does not depend on where you start or where you put your level, in this case, because we start in 0. And this should be sort of a scaling of the picture, where since we only consider being finite, the time scale does not matter in a certain sense. That would be my explanation of it. I don't know whether it makes you happy or not.
No, it's okay. I just thought it was interesting. Well, I noticed that while reading the paper, and yeah, I thought that was interesting. And I was meaning to ask as well about the last thing you mentioned about applying L'Hopital's in the proof of 3b, and I was wondering if whether, as in the way as psi, the first derivative valued at 0, being when having characterization in terms of the behavior, the syntactic behavior of x, if the second derivative being strictly positive could have some effect like that in a syntactic behavior, and that would explain why it was necessary the hypothesis, that extra hypothesis in the proof of B.
Okay, well, yeah, of course. I mean, second moment to exist means you have a variance, but well, I mean, there's also this 2 popping up here. So here's a 2, there's a 2. So there might be some relation as well. But still, we were not able to grab that, because not with L'Hopital, of course. So would be nice to. Well, it would be really nice to know more about this behavior here. But at some point we had to stop to think about it.
Okay, thank you. And well, just for curiosity, in paper, it's mentioned that maybe to build an explicit example, explicitly for the formulae given for the first moments, would be hard. And you say that in the forthcoming paper you will develop one. I was just wondering if you could tell us something about that.
Yeah, that's true. So as I said, from this formula, we were able to actually compute such moments when, for example, in the case that the Lévy process has phase type distributed jumps, because then the Q-scale function can be written down explicitly. And so you can also write down this primitive explicitly. And there are also formulas for the Laplace exponent, at least. And it's possible to evaluate that, at least. So what we did is in the second paper, so it's an archive, you can look it up, is these phase type distributed jumps, and then you can get formulas like for the first and second moment, and actually you could do it for even higher moments, but it's a lot of computational stuff. So it's a long and tedious exercise. But it works well. And once you have the formula, okay, it's fine. So that's what we did. And for exponentially distributed jumps, which are of course a special case of that, you can actually recover known results on these and then the ruin time, at least in this setting that you have a risk process for exponentially distributed claims or jumps. There were results on the moments of the ruin time. And then you can recover them from this formula. So please look at an archive for the whole picture.
Well, I meant about the paper on, I'm sorry, perturbed Kramer-Lundberg process.
Mm-hmm. Exactly. So what we do there is we only consider the case of finite jump activity, because then you have some formulas for the scale functions. If you don't, then no how to evaluate this, it's impossible. Except of maybe if you just look at a Brownian, if you just look at a Brownian motion, of course things are also known and studied. But we were more interested in the case with jumps. But finitely many of them were enough to make things complicated. And the formulas you get for these moments, they are really long, right? So you really get long, tedious formulas. So that's why I didn't want to put them here, because it's just, you look at them and well, oh, okay.
Well, thank you very much.
Are there more questions? I have one question about what you did was for a spectrally negative process you define or you find when this tau x minus is finite, right? Mm-hmm. The moment, sorry. But what you use, it is like when you hit positive x, like you have one, like you compare, instead of working with tau minus, you work with tau plus. And if you have a spectrally positive process, you will have like this kind of relationship also, no? Like if you want to know something about tau plus, you can say.
Yeah, you could just change the sign at the beginning and do the same. Yeah, it just needs to be spectrally one-sided.
Yes. And what happens if it is not spectrally one-sided? Can you decompose in two of them and then apply the same thing, or no?
I don't think so. Actually, it's gonna break down already here, because you don't have such a description, because you cannot define a scale function if you have jumps in both directions. If you don't know the scale function and you have nothing to start with.
Okay.
But of course, it would be nice to know about, but all the literature in this direction uses one-sided jumps.
Thank you. Are there more questions?
Well, maybe some about applications, because, well, I think the topic actually it claims to be used as in the motivation, in Kramer-Lundberg, I mean, in risk theory. But have you found maybe some other applications not about risk theory?
So we were mainly interested in the risk theory part. course, you might think about the dual process in queuing, although I'm not sure about how to interpret this finiteness of moments there. But it could be, I mean, it's a quite general model. You just need jumps in one direction in a Lévy model. No, but we didn't dig into that. We were happy that we could do it in such generality.
Thank you. Well, it is general.
I have a question with you in your main result, because if I remember correctly, in one of the statements you got init and only, and in the other one is only one direction. Did you explain, or could you repeat it? What is the difficulty to get the other direction in the third statement?
The problem is that actually we cannot prove, so it's really technical down here. So if you, the moment that you want to prove that this growing like of order kappa, it's down here in these parts that are in red, which means that you can only get necessity without further assumptions. And the sufficiency, so which I completely left out here. Well, at the first moment it seems like a technicality, but somehow the behavior is really different, because if you look at this process, so this psi prime of 0 is the killing rate, right? So and having it being 0 or positive changes the whole behavior, because either you have killing or you don't. And somehow this goes into these results on the Lévy process down here. And then it made it impossible to do the remaining steps for the case that psi prime is 0. So where you actually have no killing. Somehow, I mean, one would guess that without killing it, life would be easier, but here it's not.
Okay, thank you.
Thank you. Is there any other question? No. Well, I knew that Francisco has one. Okay, I can tell you. If you have done an implementation of your model, or do you know? And if you have compared with other risk model theory?
Yes. So as I said, in the classical Kramer-Lundberg model, actually this equivalency was known. So this part here in a classical Kramer-Lundberg model, that's known. And concerning the formulas that we obtained to get really the precise values for expectation or variance, we also did some implementations actually to see whether the computations were correct, because as I said, you get these huge formulas and at the end you don't know whether everything is correct. So we had to check it and double check it, and so we made also some simulations, and yes, it worked out. So seems to be okay. But of course, one cannot make simulations to check for something like this, right? Because in a simulation, ruin will happen in finite time, or you just have to end the simulation sometime. And so these such things are important to know it actually in advance before you try to simulate it.
Yes. Okay. So thank you very much, Anita. It was a really good talk.
Okay, so I will stop the share.